Alright guys, today we're going to talk about gas laws, specifically the combined gas law. This is only 8 slides, but it has 3 problems in it, so it's not going to be a 2-minute podcast. Make sure you're ready to take notes, make sure you have your calculator. We have looked at these 3 gas laws, Boyle's, Charles, and Gay-Lussac's, but notice how similar they are. Notice, for example, these 2 right here, both are over temperature. Would it be possible to combine them? And notice up at the top here, we've got P1, V1. So what we're going to do is we're going to combine these 3 gas laws into one. We're going to call it the combined gas law. Right? So please write that down. That's your combined gas law. And you'll notice that the initial state of a system, which is pressure, volume, temperature, is the same as the final state of your system, which is pressure, volume, and temperature. So we could change all 3 instead of only 2. So let's go ahead and do one. All of your rules apply. So we're going to start with my initial system, which is 20.5 liters. That's my volume. It has a temperature of 31 Celsius and a pressure of 765 millimeters of mercury. Okay, that's my initial system. And my final system, the temperature is dropped to negative 57 Celsius. Pressure is 222 millimeters of mercury, which is far less than what we started with, and we're asking for what the volume is. All right. Now, let's see, we have both temperatures in Celsius. Those have to convert to Kelvin. We have volume, which is in liters, and it doesn't specify what the volume is at the end, so we're going to use liters for that. And our pressure is still in millimeters of mercury in both cases, so we don't have to worry about that. So let's go ahead and start with temperature. Our first temperature is 31 Celsius, 31 degrees Celsius, and I have to add 273 to that. Okay, when I add 273, that gives me 304 degrees, 304 Kelvin. Now I want my second temperature. My second temperature is negative 57 degrees Celsius, and I have to add 273 to that, so I'm still going to come up with a positive number. But when I do that, I come up with 216 Kelvin. All right, so we should be able to just plug and chug here. We have P1, V1, P1, V1 over T1 is equal to P2, V2 over T2. So let's see what we have. We have our initial pressure. Our initial pressure is 765 millimeters of mercury. And our initial volume is 20.5 liters. And our initial temperature is 304 Kelvin. And now we're going to go to our final pressure. Our final pressure is 222 millimeters of mercury. And our final volume is what we don't know. And our final temperature is 216 Kelvin. Remember, we have to do all this in Kelvin. All right, so this should just be a plug and chug in your calculator. You're going to be doing cross multiplication. These 2 things up here times this temperature down here, divided by what's left. So I'll write that out. I'm only going to write this out once. No, maybe twice. 765 millimeters of mercury times 20.5 liters. Now, guys, I realize this takes time, but there's a reason I'm doing it. Right? I'm not doing it for my health. I'm doing it to make sure I get my answer right. Right? So let's see, I multiply those 3 things and divide by 304 Kelvin divided by 222 millimeters of mercury. All right. Now clearly we want our answer in liters, because that's what's left. Well, let's look what happens. We've got 304 Kelvin, so Kelvin disappears, and Kelvin disappears. And we have millimeters of mercury, so they cancel each other out, and the only units we're left with are liters, which is what we'd expect. So that helps us make sure that we get our answer correct and that our units all match up. All right? So when we do this, we will come up with a final volume of 50.2 liters. Okay, that's that problem. Hopefully you saw how to do that. Right? You should be able to just plug and chug these things in for yourself. All right, here's another one. Go ahead and see if you can do this. All right, pause the video. Yes, please pause the video and try it yourself. All right, I tend to underline things or circle things that help me as I'm doing this so that I make sure that I get all my numbers right. All right, so I have, let's see, a 15.5 liter thing that's staying at 15.5, and my Celsius temperature is changing, and I want pressure. What's the new pressure inside the tank? Again, I can go with ATMs, so those units are the same. I have to convert my temperatures, so let's just do that. Temperature 1 is equal to 15 degrees Celsius, and I have to add 273, so that's going to give me 288 Kelvin, and my second temperature is 38 degrees Celsius. And if I add 273 to 38, I get 311 Kelvin. Okay, so I'm done with that. So I have, let's see, P1 V1 over T1 equals P2 V2 over T2. So my initial pressure is 45 atm. And my initial volume is 15.5 liters. And my initial temperature is 288 Kelvin. And my final volume, my final pressure is, what's the new pressure? I don't know. So that's going to be in ATMs, because my units have to be consistent. And I'm at 15.5 liters. And I'm at 311 Kelvin. Right? So now I should be able to cross multiply 45 ATMs and 15.5 liters and 311 Kelvin. I'm going to divide that by 288 Kelvin and 15.5 liters, and that's going to give me 48.6 ATMs. Okay, I'm done. Did you notice anything? Did you check your units to make sure you could cancel your units, like your Kelvin here, and your liters here? Did you happen to notice, this is what's really interesting, is that your liters didn't change. Your volume didn't change. So I didn't have to include volume in my calculation. I could have gone with P1 T1 equals P1 T2, P1 over T1, right? Which is Gay-Lussac's law. So I could have used that instead of the combined gas law. So here's something to understand and to notice. If your volume remains constant, then you can just throw it away. You don't even have to put it in there. You can just treat it as if it's 1 because it's completely unnecessary. Right? That's true for pressure or temperature as well. Right, so notice that sometimes you have information in the problem that you don't need, right? Because your pressure in this case, your volume in this case, just remain constant. Okay. We have one more problem, right? And I'm going to let you set it up, so pause the video and see what you can do here. All right. I notice I've got liters at the beginning, and it's changing to 17.4 liters at the end, so my volume is changing. I have pressure at 241 kPas, and I'm asking for the new pressure in the tire, so that's changing. And I'm starting at 5 degrees Celsius, and I'm changing to 48 degrees Celsius, so temperature's changing. Everything's changing, so I have to use P1 V1 over T1, my combined gas law, is equal to P2 V2 over T2. Right? My temperatures always have to be in Kelvin, so let me just start with that. So T1 is equal to 5 degrees Celsius plus 273 gives me 278 Kelvin. And my second temperature is 48, T2 is 48 degrees Celsius. And I have to add that to 273 Kelvin. and that's going to give me 321 Kelvin. Okay? What else do I notice? Did you notice that your pressure is given to you in kPa and that we want pressure in psi at the end? All right, so let's go ahead and do the problem in one or the other. Right? I don't know how you did it. I'm going to just choose to leave it in kPa and do my work there. Right? And I'll eventually convert 2 millimeters to psi. All right, so I start with my initial pressure, which is 241 kPa. My initial volume, which is 17.3 liters. My initial temperature, which is 5 degrees Celsius or 278 Kelvin. All right, my final pressure is an unknown, and that's going to be in kPas. Again, my units must be consistent from here to here. It doesn't matter what they are, so long as they're consistent, just like we were doing Boyle's and Charles and Gay-Lussac's law. So long as we're consistent, we're okay. And our new volume is 17.4 liters. And our temperature, that's changed significantly. That's gone up to 321 Kelvin. Right? So, if you did not do this on your own, pause the video here, see if you can do the math. All right, the math here is 241 kPa times 17.3 liters. We are simply plugging and chugging here. 321 Kelvin divided by 278 Kelvin divided by 17.4 liters. Our liters cancel, our Kelvins cancel. I'm left with kPas as my units. When I do the math, I come up with 277 kPas. Now on my calculator, guys, I have many more significant figures than this. And frankly, when I continue my problem, I do that. I don't round here and then round again at the end. I'm actually using the long number, and I just keep on going. I'm just too lazy to write it out. But now what I have to do is I have to convert from kPas to psi's. And that means I have to go to ATMs in the middle. So if we go to what we had in our last podcast, to do those, or 2 podcasts ago where we were doing conversions, we have 277 kPa, and we have to convert from kPas to atmospheres, and then we convert from atmospheres to psi. And 1 atmosphere is 101.325 kPas, and 1 atmosphere is 14.70 psi. When we do the math, we get 40.1 psi. Now guys, you could have done this the other way. You could have converted from kPas up here to psi originally, and that would have given you about 35 psi to start. And then you could have worked through your problem, and you still would have come up with 40.1 psi as your final answer. Okay? So guys, really what this is all about is thinking the problem through first. All right? So here's your combined gas law. Now you don't ever have to use Boyle's, Charles, or Gay-Lussac's law because your combined gas law actually does it all. Right? That's kind of nice to know. All right. So we're done. Go ahead, go off and do the worksheet. Again, they get progressively harder as you go along, so make sure that you work all the way to the end of the worksheet. And if you have questions, we'll see you in class. Come ask us for help. We'll be happy to help you. All right? See you then. Bye-bye.